Okay, good morning, everyone. Today we will begin chapter 4. Chapter 4 is going to go by quickly. There's a lot of theory involved, concepts, but I'll go over the theory and the concept. And then what I want you to do is actually, well, I will say that don't take down too many notes during this, the equations, the derivations. There is, if I summarize this, there's only one equation for the entire chapter. So again, I want students to kind of like pay attention and just listen to, listen to the talk, and then of course ask questions as we go along. But do not worry about the derivation. Do not worry about writing down, any of the quantities in there. There's only one standard equation, and then two sub-quantities. Okay, so let's begin. All right. So the name of the chapter title is Transients. The reason is because we are looking at the energy transfer phase for an inductor and a capacitor. Okay, so if you recall back to the beginning of chapter 3, I stated capacitors and inductors are energy storage devices. So they receive energy and they store it, and they later release the energy back into the circuit at a later point in time. So what we'll study here is the determination of the voltage and current values during that energy transfer phase. Okay, during that energy transfer phase. When the energy is being transferred into, or they are receiving the energy, we say that they are being charged. And when the energy is being transferred out, we say that they are being discharged. Okay, so energy flows into the capacitor and inductor. We say it's being charged. Energy flows out. We say they are being discharged. The analysis during these phases is known as transient analysis, because the response is transient. It is fleeting. It is momentary with time. Okay, it's momentary with time. Transient response will be of two kinds, but the graph or the response structure remains exactly the same, no matter what component we're talking about, no matter which circuit we talk about. So it doesn't matter whether it's inductor, doesn't matter whether it's capacitor, doesn't matter whether it's charging or discharging. It always has an exponential relationship with time. During charging phase, we start from 0 and we go up to our maximum value. And then in the discharging phase, let's see. Discharging phase follows a similar pathway. And you again have a exponential relationship with respect to time. Okay, so both of these are showing the charging waveforms. This is the discharge. Okay, time is here. This could be describing voltage or current, but they always have an exponential relationship with time. Okay, transient response is the response before it reaches steady state. Steady state is when it reaches full charge. So if you think back to chapter 3, right, you apply a voltage, you apply a current, starts receiving the energy. After a certain point, it receives all the energy that it has the capacity to store. And then from that point on, we reach a condition known as steady state. Steady state applies to both DC as well as AC. Okay, right now we will deal only with DC. Okay, we are not going to go too deep into AC transient responses. But after a certain point in time, the voltage and current for the inductor and capacitor does not change with respect to time once it reaches full charge. So that is known as the steady state response. In the graph, it is known as the steady state region. Essentially, steady state simply means it's either reach full charge or full discharge. Right? Full discharge, it goes all the way to 0. The response is not changing anymore. So I like to call that also a steady state. But in general terms, steady state refers to the charging phase. Transient response is the response between, when the time when you begin applying your voltage or current till the time it reaches steady state. And that is what we will study. So I stated that it's only one equation for the entire chapter, and this is the reason why. Okay, it doesn't matter which component you take, they all have an exponential relationship with time. And so it is the exact same equation. We will look at 4 different circuits, but the equation will turn out to be exactly the same for all 4. Okay, transient responses are of 2 kinds, natural and forced. Ignore the negative connotations of the word forced, okay? It's nothing sinister about it. It simply means that the response of that component is due to an externally applied energy source. Hence, the response is being forced from the component. A better word for it is a step response. Okay, it says natural and forced response. Natural is basically the capacitor or inductor has stored some charge, and then the energy is just being discharged, and so there is no externally applied source that is forcing that voltage or current. Charging, you're applying an external voltage or current, meaning you're connecting a voltage source or a current source, and that elicits a response in terms of voltage or current from the capacitor or inductor. If you think about it, everything that we have studied so far, when we connect a voltage source or a current source to a resistive network, is basically a forced response. Okay, so again, natural response is basically when it has the naturally stored energy and it's being discharged. So the discharging of stored energy is natural response, and forced or step is due to an externally applied energy source. Okay, essentially we're studying 2 kinds of circuits, charging and discharging, for 2 components. And so based on that, we have 4 circuits. So we have, okay, go back, sorry. Step response or forced response, where you have a source connected to the components, right? You have a source connected to the components, whether it's a current source or a voltage source. These are both voltage sources, and these are both current sources. This right here shows you the application of the Thevenin and Norton equivalent circuits. If you have a capacitor or inductor connected to a circuit, similar to a resistor, if we need to find the voltage or current that is being applied to that component, then we need to find the Thevenin or Norton equivalent circuits for that component. Okay. But again, this is a non-E major class. So again, we will look at circuits, but nothing too complicated in terms of determining like a Thevenin or Norton equivalent. So these are the charging, and then these are the discharging. Okay, discharging simply means you take your inductor or capacitor and it is being discharged through a resistor. Okay, charging also, you have a resistor in the circuit. If you note, all of them state EQ. So EQ simply means that there is a possibility to reduce all components down to one single equivalent component. Okay, it's one single component. Now, you could have multiple inductors in a circuit, you could have multiple capacitors in a circuit, but if it is possible to reduce all of them down to one single inductor or one single capacitor, we still call it a one inductor or one capacitor circuit. Okay, and then this is important. Each energy storage device requires a first order differential equation at its solution. Okay, first order differential equation. And because it requires a first order differential equation, we refer to it as a first order circuit. If you have one energy storage component in your circuit, it is known as a first order circuit. Okay, so all of these are first order circuits. because you have one energy storage device. Now, physically, these devices could be 10 or 100, but electrically speaking, if you can replace them with one single equivalent inductor or component, then it's still a first order circuit. If you have more than two, if you have more than one, second order, third order, so on and so forth. Okay, we'll only look at the first order for now. Second order gets into a whole different analysis. So, if we have time, we'll look at second order at the end of the quarter. But for now, we'll just look at first order circuits. So based on these four circuits, we look at four different responses, right? Natural response for inductor and capacitor, and forced response for the inductor and capacitor, charging and discharging. So in the setup of this circuit, you have a current source. That current source is supplying energy, right? Before time t equals 0. So the way to read this is you look at the time. So it says time t equals some value. And prior to that, the switch was closed. What it is indicating is that at time t equals 0, the switch is flipped open. Okay. So that means you have to infer that for time t less than 0, the switch was closed. Okay, the switch was closed. And at time t equal to 0, the switch is flipped open. When the switch is flipped open, the circuit breaks. Right? The circuit breaks. So the only thing left in the circuit is the inductor and the resistor. So prior to time t equal to 0, inductor was connected to the current source. We don't know how long it was connected. We don't really care. It simply states it was connected for a very long time. That means we have to assume that it has reached steady state. So if you read the words a long time, those words indicate that the component is at steady state. Whether the steady state could be fully charged or it could be fully discharged. In this case, we can see that the switch was closed, and the current source was connected to the inductor. So the current source has transferred energy to the inductor. The inductor has captured all of the energy that it needs, or that it has the capacity to store. It has reached steady state. At steady state, inductors behave like a short circuit. And because it's behaving like a short circuit, everything is flowing through that inductor. Nothing is flowing through that resistor. Okay, inductor is fully charged. At times t equal to 0, switch is flipped open. Circuit reduces to a single inductor and a single resistor. So now here's the derivation. Again, we are not going to do the whole derivation. You simply need to understand the concept and then know how to apply the equation. So the inductor is fully charged. The fully charged inductor will have some current flowing through it. That current, if you remember from the previous slide, we just saw in the previous slide, the current source was connected to the inductor. The inductor is behaving like a short circuit, meaning the total current that is flowing through the inductor has a value of IS. And so we are analyzing the circuit not before time t equals 0. We are analyzing the circuit only after the switch is flipped open. Again, so this is a crucial difference. We do not care about what happened before the switch was open. Okay, let's take a pause. So again, as an engineer, if you're analyzing something, you're only analyzing after a certain period in time. Sometimes it may be explicitly stated that we are analyzing between, again, going back to the previous example, is 59th minute and the 60th minute. In this case, we represent that by the switches flipping open or flipping closed. That's what we signify. So when the switch is flipped open, that's when we begin our analysis. We don't care about what happened previously. But we look at the previous conditions in order to set up our problem for the present analysis. So previously, the current that was flowing through the inductor was IS. It had a value of IS. If it has IS, then we can begin our analysis. Okay. Now, here's a concept that you would need in order to set up your problem. We have t equals some value. When we begin analysis, we say it's t equals to 0. Then we can refer to t minus and t plus. T minus simply means the time right before, and t plus means the time right after. It doesn't have a specific value. Okay, it simply means right before and right after. Again, it does not have a specific value. Okay. When it says t equals 0 minus, it simply means the time right before 0. And 0 plus means time right after 0. And this is important because the current through an inductor cannot change instantaneously. Because it cannot change instantaneously, we say that the current through the inductor right after the switch is flipped is the same before the switch was flipped. And this allows us to infer or assume that the initial current through the inductor is IS. So let's take a pause. You think over that concept. Let me know if you have any questions. Any questions? Okay. So again, t equal to 0 minus is right before 0, and 0 plus is right after 0. Right before 0 and t equals 0 plus is right after 0. It simply allows us to make this assumption, without which we would have no idea what the energy in that inductor is. So if we look at the circuit right now, nothing is given to us. We have no idea what the value of current for the inductor is. Okay, so we assume that from the previous state. We are not analyzing the previous state. We are simply using the previous state in order to set up our analysis. So at the top, we apply KVL. KVL simply would give us VL plus VR equals to 0. Inductor voltage plus resistor voltage should equal to 0. You plug in the values of the equations. Inductor voltage is L di over dt. Resistor voltage from Ohm's law, I times R. We solve this first order differential equation, and you obtain a solution that looks like this. I of t is given by I0 into e raised to minus t over tau. There are a few steps in the middle. Again, for EE major classes, we do show the derivation. Non-E major classes, we just skip through those. Okay. Now, the structure of this equation is exact. You will see when we get to the end that you can take that standard generic equation and not have to use this. But if you look at this equation, let's break down the terms. We have I0, we have tau, and those are the only two variables. I mean, two quantities. Okay. I0 is the initial current in that inductor. It's basically signifying the energy level of that inductor when it begins discharging. And again, going back to the previous slide, the previous two slides, the reason we set up about 0 minus and 0 plus is to determine the value of I0. So this is the value at time t equals to 0. Sometimes it is also referred to as subscript II, initial value. Both of them are valid. You might see it as subscript I or 0. Both mean exactly the same thing. The initial value when you begin your analysis, or the value at time t equal to 0 when you begin your analysis. Okay. T is the variable. Remember, this response is transient, right? So at any given point in time, the value of that current or that voltage is different. So the final equation we get is always as a function of time. I of t is I0 into e raised to minus t over tau. Tau is the time constant. It determines how fast that energy is being transferred. In this case, the inductor is losing the energy, so it's describing how fast the energy is being lost. It's a constant, and it depends on the size of the bucket and the pipe dimensions. Okay, basically the resistor and the inductor is given by L over R. Time constant is independent of the circuit. Whether it's charging or whether it's discharging, our L circuits, resistor inductor circuits, will always have a tau that is L over R. That does not change. Okay, it's a fixed value depending on the size of the inductor and the size of the resistor. Okay. All right, any questions? Then we can take that standard expression we found for I of t, plug it into standard Ohm's law. You can find voltage as a function of time. Simply multiply it with the resistance, R times I of t, and you get R into I0 e raised to minus t over tau. Okay, voltage found simply from Ohm's law. Expression for power, P is IV, or I squared times R, or V squared over R. In this case, we have the inductor current equation, so we use I squared times R. So all of the energy will be dissipated through that resistor, right? Resistors will receive the energy and dissipate it as thermal energy or as heat. So all of the energy that is lost in that resistor has to equal the energy that was stored in that inductor. And so the energy dissipated in that resistor is half Li square. Same equation we studied in chapter 3. No difference. Okay, half Li square. That is the total energy that was stored in the inductor. And then, of course, eventually, the inductor loses all of that energy through the resistor, and it goes to 0. Remember what I said at the beginning of chapter 3? Real life inductors and capacitors cannot store that charge indefinitely. Ideal inductors, we can assume yes. Real life, no, because it will dissipate the energy through itself. Okay. In this case, we can model a real life inductor with that resistor and state that it's just losing the energy through itself. Okay, questions? Any questions? Does the theoretical concept make sense? Mathematical will make sense kind of at the end of the chapter, but does the theoretical concept make sense? Okay. Capacitor natural response. Now we'll think in terms of voltage. Different structure for the switch, but the functionality is the same. When it was at position A, capacitor was charging voltage VG. Generator voltage is connected to that capacitor. Capacitor charges to a level of the source. So capacitor voltage VC is equal to VG. At some point in time, capacitor reaches full charge. After that, the switch flips to position B. The generator is disconnected. Capacitor is connected to resistor R. No more source in the circuit. If there is no more source present in the circuit looks like this. A fully charged capacitor connected to a single resistor. So we have one capacitor, one resistor. We have a first order circuit again. When we go through the analysis, again, we need what the stored energy of that capacitor is. To do that, we look at time before the switch was flipped. And so before the switch is flipped, we know that the capacitor is fully charged, hence it behaves like an open circuit. If it's fully charged, the value of the capacitor, VC, should equal VG. Capacitor voltage VC is equal to the source voltage VG. After the switch is flipped open, capacitor voltage cannot change instantaneously. So at the beginning of our analysis, we look at the time or the value of the voltage before the switch was flipped. Because it cannot change instantaneously, we can state the voltage across that capacitor after it is disconnected from the source is the same as the voltage before it was disconnected from the source, because it cannot change instantaneously. So again, this is a very important concept. I want to make sure or ensure that every student understands this. Okay. Current through an inductor and voltage across a capacitor cannot change instantaneously. Energy transfer cannot take place at the snap of a finger, right? And so you have to look at the circuit prior to the switch is flipped. That will allow you to set up the initial values for your analysis. Questions? Okay. So we have the capacitor voltage connected to the resistor. You apply KCL at the top. KCL should give us capacitor voltage plus capacitor current times the resistor current should sum up to 0. Don't worry about the signs. You plug in the equations for the resistor and the capacitor current, C dV over dt in terms of the applied voltage. And for the resistor, simply Ohm's law, IR. Sorry, V over R. V over R. You plug in those equations, you get a first order ordinary differential equation. Greater minds have come before us and solved this equation, so we don't have to, right? So we have the solution given to us. If you look at that solution, it follows the exact same structure that we had for the inductor discharge equation. Capacitor voltage as a function of time is V0 into e raised to minus t over tau. Exactly the same equation, no difference. The structure is the same. The only two quantities are V0. V0 again is the voltage when you begin your analysis. Could be V0 or VI. V0 or VI. Okay, V0 or VI. So again, 0 simply means the time you begin analysis. I stands for initial. Can be used interchangeably. Tau in this case is the product of the resistor and the current. Tau for the inductor was different. Tau for capacitor circuit is different. In this case, it's very easy. Product of capacitor and the resistor, RC. Sometimes it's also referred to as the RC time constant. Okay, RC time constant, product of the resistor and the capacitor. And that's it. As straightforward as that. This tau remains the same for charging as well as discharging. Okay, that doesn't change. Okay, capacitor current equations. Again, from Ohm's law, you have I of t. And so you simply apply Ohm's law, you get V over R. And you can find the expression for I of t of the capacitor. Instantaneous power, since we have the voltage, we can apply V squared over R. And you find those equations. Total energy dissipated in that resistor has to be equal to the total energy that was stored in the capacitor. And it comes out to be half CV squared, the exact same that we saw in chapter 3. No difference. Half CV squared. Okay. Let's take a pause. Let me know if you have questions. Any questions? Okay. So I'm going to skip on this summary. We'll come back to this later. Actually, it won't matter because once you look at the generic equation, the procedure is exactly the same. So step response, everything exactly goes, everything is exactly the same as the discharge. What we have is, we have a inductor or a capacitor that has no charge on it. We assume that it has zero charge. We then connect it to a source. The current starts flowing through the inductor or the voltage being applied across the capacitor. In both cases, we can define the initial energy of the inductor. If it's not given to you, simply assume it to be zero. If it says that the switch was open for a very long time, we can assume it to be zero. Initial energy equal to zero. And again, for non-E measure classes, we don't do any of the multi-switching levels. So in E classes, we might do like, switch has like 3 or 4 different positions. At position 0, component is completely discharged, doesn't have any energy. Then it starts charging to a certain level, then discharges to half the level, then starts charging again, back and forth, back and forth. But for non-E measure classes, we just do standard charging from like 0. So procedure for the derivation, same. Apply a KVL around the loop. In this case, we again have VL plus VR, but this time, because it's charging, VL plus VR is not equal to 0, it's equal to the voltage source. And voltage source is Vs. That's the only difference. So you again obtain a very similar differential equation, you solve it, and we obtain a structure that looks like this. IF plus I0 minus IF into e raised to minus t over tau. There is I0 in this equation. We have to take the initial current into account. But if the initial current is equal to 0, meaning if it's a fully discharged capacitor, then you don't have to worry about anything. The equation reduces to simply IF minus IF into e raised to minus t over tau. Okay. So again, most cases, I0 would be equal to 0, and you would not have to worry about taking that into account. Tau still remains the same, L over R, no change. Okay, it depends on the value of the inductor, depends on the value of that resistor. Final value of the current can be determined from the voltage source. So Vs divided by R, that would give you the final value. Remember, this is charging, right? So if it's charging, you need to know the final value. That final value will always equal to the energy that is being supplied by the source. If it's a current source, you can simply take the current. If it's a voltage source, you simply apply Ohm's law and you find the final value of that current. Right? Because eventually the inductor will behave like a short circuit. The structure of this equation is exactly the same as the previous ones, except there are one or two more quantities in there. And then RC step response, exactly the same. And I keep repeating exactly the same, exactly the same, exactly the same. And you will see that at the end. Okay. So you have a voltage that's being applied. Initial conditions, of course, depend on the initial energy of that capacitor. If it's not given, again, assume it to be zero. Capacitor is charging from completely zero or discharge conditions. Current source is connected, IS. It could be a voltage that is connected, doesn't really matter. It's applied, you apply KCL at the top. You again have capacitor current and the resistor current summing up. Instead of being summed up to zero, it's now summed up to IS. You get a first order differential equation. You solve that, you obtain. And again, being repetitive here, but you get exactly the same equation. Voltage as a function of time is Vf plus V0 minus Vf. Same thing here. If it's fully discharged and V0 is 0, then it simply becomes Vf minus Vf into e raised to minus t over tau. T is the variable. Tau is the time constant, product of the resistor and the capacitor. So again, whether it's charging or discharging, it doesn't change the time constant. So this is the only equation you need. This is the only equation you need. You don't need anything else. Okay. X of t, excuse me, X of t is xf, the final value, plus x0 minus xf e raised to minus t over tau, where x is current or voltage. Okay, X can stand for both current as well as voltage. You find the initial conditions. Okay, you find the initial conditions. If the circuit is being discharged, then the initial conditions, meaning X0, will have the value of a fully charged capacitor or a fully charged inductor. Okay. If it's discharging, then XF will always be 0. No questions. If it's a discharging equation or a discharging circuit, the value of XF is always 0. It doesn't matter if during the discharge, that discharge portion gets interrupted and it starts charging again because you applied another source. When you plug in the equation, you always plug in XF equals to 0. That's it. So if it's a discharge equation, if you recognize the circuit as being discharging, XF will always have a value of 0. Then the equation reduces to this structure. It becomes simply X0 times E raised to minus T over tau. Because XF is 0, so it becomes X0 into E raised to minus T over tau. If you look or you compare this to the equation we obtained here, what did we obtain? X0 into E raised to minus T over tau. Same structure. Does everyone see that? And that's why I said you only need one equation. So you only need one equation, nothing else. Your job as an engineer, when you try to solve this kind of transient response, is to recognize the circuit. And again, there is not much of circuit analysis in here in the sense that you're not performing like massive calculations. Okay. What you will do is you need to recognize the circuit, understand what the problem statement is asking of you, understand what it is giving you, set up your initial conditions, meaning find the values for x0, find the values for xf, and then simply plug it into that equation. That's it. That's all you need to do. So setting up the problem in this case is not just like 50% of the work, it's almost all of the work. Okay, because after you set up the problem correctly, plugging in the values and performing a calculation is rather straightforward. So this is the most important. You determine the initial conditions, find x0. Okay, finding x0 simply means you have to understand what the circuit is telling you. You have to understand what the words of the problem statement are telling you. You set up the problem, find x0, then find xf. If it's discharging, xf is always 0. If it's charging, then xf is the value of the source. But if the source is not connected directly, then it's the value of the Thevenin or the Norton equivalent. Okay. I'll give you an example. Let's see. Let's finish this first. Oh, find the time constant from these two equations, right? Tau is L over R or tau is RC. That doesn't change. It remains exactly the same for all circuits. If it's an RL circuit, it's L over R. If it's RC, it's R times C. And then directly plug those values in that equation. That's it. So this equation has three quantities, x0, xf, and tau. That's it. You have to determine these three and plug it directly into this equation. So let's take a pause, you think over all of that, and let me know if you have any questions. Any questions at all? Did the theory make sense? Did the concept make sense? If you're interested in the derivation, you can stop by my office. I can, give you the derivation. If anyone is interested in solving the differential equation, I can show that to you. I have multiple books on those. But again, as far as solving this, again, as an engineer, especially as a non-EE engineer, if you're looking to solve this, then you need to find three values, the initial, the final, and then the time constant. And so it's important to recognize that circuit. Okay. So let me address point number one. It says find the equivalent circuit, right? So what does it mean? Let's say I have a circuit like this, voltage source being applied to this capacitor. Eventually, that capacitor voltage will equal the source voltage, Vs, right? Vc will equal Vs. And this is R, or let's say R1. So my time constant tau will be R1 times C, right? Easy enough. But what if it's no longer a single resistor? This is R1, R2, and Vs. Is the capacitor voltage still Vs? No, because it's not being applied directly, because some of the voltage will go across R1, some of the voltage will go across R2. So it's not the same, right? So in that case, we have to find the equivalent circuit, which is a Thevenin or Norton equivalent circuit as seen by the capacitor. Meaning you have to analyze the circuit by removing the capacitor and analyze it between those open terminals. Okay, so you have to remove the capacitor from your analysis. These becomes A and B, and you find the equivalent circuit between A and B. Okay. And so Vs would be different. And the voltage that is being applied to the capacitor will be the Thevenin equivalent voltage. Now, in a quiz or in a final exam, I'm not going to ask you to solve like a long, big circuit. But you should understand this concept. Okay, Vs is not being applied directly to that capacitor or to that inductor. So you have to find the Thevenin and Norton. So this is a use case scenario where we actually use, and why Thevenin and Norton is so important for circuit analysis. Again, the concept of Thevenin and Norton is not an analysis technique, it's a concept. And this is the reason why it's so important. Okay, universal time constant chart. Doesn't matter what kind of circuit it is, it will always have this kind of exponential response, right? E raised to minus t over tau is common for all circuits. And so this is for charging, and this is for discharging. E raised to minus t over tau will take on a standard value. If you plug in values of t as 0, 1, 2, 3, 4, 0 tau, 1 tau, 2 tau, and so on and so forth, meaning as a multiple of the time constant. Obviously, t can take any value, 0.01, 0.0001, 0.0005, could be any value. But if you plug in t as a multiple of tau, the time constant, you'll always have a value mathematically. And that will always follow this kind of curve, same exponential curve. The only thing that will change is the starting and the ending point, right? So the values are listed in this table here. Okay, the values are listed in that. The values are listed in this table here. When t, meaning the time that is taking either to charge or to discharge, is equal to 1 times the time constant, 1 tau. If it's charging, it tells you that it acquires 63% of its charge, of its final value, after just 1 time period. So there's a big jump. It's exponential, right? So there's a big jump right at the beginning. So in a very small period of time, it acquires more than 50% of its final value. Does that make sense to everyone? And then on the other hand, if it's discharging, then it loses more than 60% of its value within the first time constant. Again, exponential, so there's a big jump right off the bat. Okay, so it loses this value within that first time constant. So whether it's charging or discharging, again, it follows that same pathway, the same curve. This table here simply lists how much energy is being gained or lost after each time period. This is a mathematical expression, e raised to minus t over tau. So if you plug in values of t as, I don't know, like 1 million seconds or 1 million minutes or 1 million days, you would still, mathematically, you will still obtain some value for that current or voltage, right? It could be like 0.000000 something, but mathematically, you would still obtain some value. So where do you put an end to your calculations? Well, by standard convention and accepted practice, we put an end after 5 time constants. After 5 time constants, the value across that capacitor or inductor reaches more than 99% if it's charging, or it loses more than 99% if it's discharging. So after 5 time constants, we say it's either fully charged or fully discharged. So we put an end after 5 time constants. That's standard accepted practice. Okay. Standard accepted practice, standard accepted convention. Mathematically, again, you will keep receiving an answer. Doesn't matter what value of time you put in. Okay. Right on the dot, 10 o'clock. Next class, we'll look at the examples. Quiz on Monday will be based on chapter 3, not on chapter 4. Okay, only on chapter 3, and most likely it will be piecewise linear analysis. There are extra examples on the website under slides. Please look at those. Okay, there is a PDF that's been there since the beginning of the quarter. There are 2 more examples of piecewise linear analysis. Please review those because that's going to be on the quiz. Piecewise linear analysis. All right. Have a good weekend. I'll see you all on Monday. Yes.